Right now, numbers are moving quietly through almost every part of your life. They are keeping time on the clock beside you. They are guiding electrical signals through the device playing this video. They are measuring the distance between planets, recording the rhythm of your heartbeat, storing music, images, words, and memories, and helping machines decide what appears on your screen next. Yet numbers were not waiting for humanity in the form we know today. There was once a world with no written digits, no zero, no negative values, no fractions written on a page, and no symbol for infinity. There were animals, seasons, tools, debts, distances, and stars, but there was no familiar way to compress all of those quantities into a few marks. Somewhere in the deep past, a person made a scratch on bone or wood to remember one event. Then another scratch for another event. Much later, people began grouping those marks, replacing them with symbols, and allowing the position of a symbol to change its value. Over thousands of years, the need to solve one problem after another pushed numbers into forms that earlier generations would have found impossible. A mark became a count. A count became a symbol. A symbol became part of a written system. An empty place became zero. A debt became a number below zero. The diagonal of a simple square revealed a quantity that no fraction could express. Algebra created numbers built from the square root of a negative value. And in the modern world, nearly everything we see on a screen is translated into long patterns made from only 2 digits. How did this happen? Why did humans begin counting at all? Did people understand quantity before they had number words? Why did so many cultures build their systems around fingers, while others counted by 20s, 12s, or 60s?
Why was zero so difficult to accept when it now seems so simple? Why did mathematicians resist negative numbers, irrational numbers, and complex numbers, even while those strange ideas kept producing correct answers? And how did methods created for grain, livestock, land, and taxes become the language of physics, computing, finance, navigation, and modern science? To answer those questions, we have to travel back before cities, before writing, and perhaps even before language had words for exact numbers. Imagine a small human group living many thousands of years ago. There are no calendars on the wall, no numbered streets, no prices, no written records. The people in this group still live in a world full of quantity. They know whether a basket holds little food or much food. They can see whether several animals are approaching or only one. They understand whether everyone has returned to camp. They notice that one pile is larger than another.
This kind of awareness does not require formal mathematics. Many animals can distinguish between small quantities. A bird may notice that eggs are missing from a nest. A hunting animal may choose between a smaller and a larger group of prey. Experiments suggest that several species can compare approximate amounts, especially when the difference is large. Humans inherited this basic sense of quantity, but eventually carried it much further. The first important step was probably not the invention of a word such as 5 or 10. It was the ability to recognize that very different collections could share the same quantity. 5 stones do not look like 5 fish. 5 people do not sound like 5 drum beats. 5 days cannot be placed in a pile. Yet all of them can share something abstract. They can all be 5. That idea is so familiar to us that its difficulty is easy to miss.
A child growing up in a world filled with number words, printed digits, clocks, prices, and counting games learns it early. For the first people who developed exact counting, the idea had to emerge from repeated experience. Before a number could become an abstract concept, people could match one thing with another. Suppose a group leaves camp to hunt. One pebble is placed in a pouch for each person who leaves. When the hunters return, one pebble is removed for each person who comes back. If pebbles remain, someone is still missing. No number word is necessary. The group does not need to say that 7 people left or that 2 have not returned. The pebbles preserve the relationship. Each object stands for one person. This is called one-to-one correspondence, and it lies beneath the entire idea of counting. When a child points to objects and says one number word for each one, the child is building the same relationship. One word is matched to one object. If an object receives 2 words, or 2 objects receive 1 word, the count fails. Long before written arithmetic, people could use fingers, stones, shells, knots, sticks, or marks to create these pairings. Imagine a herder watching animals leave an enclosure at dawn. For every animal passing through the gate, the herder moves one pebble from one side of a container to the other. In the evening, the process is reversed. If every pebble returns to its starting place, the whole herd has returned. The pebbles are not yet written numerals. They may not even represent a general number. Each pebble is tied to a particular animal in a particular situation. Still, something powerful has happened. The herder has moved information outside the mind. Memory is no longer carried only in the brain. It has been placed into objects. That change may seem small, but much of civilization will eventually grow from it.
Writing, accounting, diagrams, maps, and computer memory all depend on the same broad idea. Information can be stored in a physical form that lasts after the original event has passed. A row of marks can remember what a person might forget. Some of the oldest objects linked to early counting are bones and pieces of stone covered with notches. Their exact meanings are often uncertain. A set of scratches might record animals, days, lunar phases, exchanges, successful hunts, or something entirely different. Archaeologists can examine the pattern, the age, and the context, but they cannot ask the person who made it. One famous object is the Lubombo bone, discovered in southern Africa. It is tens of thousands of years old and carries a series of notches. Another is the Ashango bone, found near Lake Edward in Central Africa and usually dated to roughly 20,000 years ago. Its marks are arranged in groups along several columns.
People have proposed many interpretations of those patterns. Some see evidence of doubling. Some notice groups related to odd numbers. Others have suggested lunar counting or simple, practical record keeping. Claims that the bone proves advanced knowledge of prime numbers are debated because patterns can look meaningful even when we do not know the maker's intention. The uncertainty matters. The marks show organized attention to quantity, but we should not turn every ancient scratch into a modern equation. The safest conclusion is also the most important one. People were deliberately grouping and recording marks long before formal writing appeared. A tally is one of the simplest recording systems imaginable. One event receives one mark, another event receives another mark. The method is direct and reliable for small quantities. It also contains a serious weakness. Suppose you have 3 marks. You can recognize them quickly. Suppose you have 8.
You may still count them without much trouble. Now imagine 50 marks in a long, unbroken row, then 500. The system still works in theory, but it becomes slow and easy to misread. The person recording the amount has saved the information, yet recovering that information takes too much effort. This creates the first major pressure in the history of written numbers. How can quantity be compressed? People began grouping marks. Instead of writing a continuous line of identical strokes, they could arrange them in sets. A diagonal line might cross a group of 4 strokes to indicate a complete group of 5. Spaces could separate groups of 10. Different shapes could represent larger units. Grouping changes the task. A person no longer has to count every mark from the beginning. The eye can recognize complete groups and then combine them. This is where the human body becomes especially important. We carry a counting device everywhere we go. Most people have 5 fingers on one hand and 10 fingers across both hands. Fingers can be raised, lowered, touched, and paired with objects. They are visible to other people, which allows a count to be communicated without a permanent record. The connection between fingers and numbers appears in languages and number systems across the world. Our modern decimal system, built around groups of 10, is almost certainly related to counting on 10 fingers. That does not mean every culture counted in exactly the same way. Some systems grouped by 5, reflecting one hand, others grouped by 10. Some use 20, including fingers and toes. Traces of base 20 survive in several languages. French, for example, preserves an expression based on 4 20s for the number 80. Other societies developed systems related to 12. A person can use the thumb to touch the 3 finger bones on each of the other 4 fingers. This gives 12 countable positions on one hand.
The fingers of the other hand can then track completed groups of 12, allowing a person to count as high as 60 on 2 hands. This may help explain why 12 and 60 became important in trade, measurement, and timekeeping, although historical systems rarely come from a single cause. 12 is convenient because it divides evenly by 2, 3, 4, and 6. 10 divides evenly only by 2 and 5. If goods must be shared among several people, a group of 12 is often easier to divide into equal parts. 60 is even more flexible. It divides evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. That practical divisibility would later help a base 60 system flourish in Mesopotamia and leave a permanent mark on the way we measure time and angles. The body offered a natural framework, but counting methods could become far more elaborate. Some communities used parts of the entire body in a fixed sequence. A count might begin with the fingers, travel along the wrist and arm, reach the shoulder and head, and then continue down the other side. Each body part served as a position in an ordered list. Such systems reveal an important principle. Counting does not require written digits, it requires stable order. To count accurately, a community needs a sequence of signs or words that always appears in the same arrangement. The exact sounds may differ, but the order must remain fixed. The word used after 4 must always be the word used before 6. Once the sequence is stable, it can be matched to objects. A complete counting system also requires one more idea. The final word spoken must stand for the quantity of the entire collection. When a child counts 1, 2, 3, 4, the word 4 does more than label the last object touched. It tells how many objects there are altogether. This seems obvious to an adult, but young children often learn the sequence of number words before they understand this rule. They may recite the words like a song, while failing to connect the last word to the size of the group. Humanity may also have developed counting in stages. Some languages have historically used only a few exact number words, with broader terms for larger quantities. A language might distinguish 1, 2, and many, or possess exact words for several small amounts, and then shift into expressions meaning a group, a large amount,
or more than can be easily counted. This does not mean the speakers are incapable of understanding quantity. People can compare amounts, use one-to-one matching, and perform practical exchanges without a long list of exact number words. Exact arithmetic becomes much easier, however, when a language offers a stable verbal sequence that can grow. Number words themselves often preserve old counting strategies. 11 and 12 in English have forms that do not follow the later pattern of 13, 14, and 15. Their unusual shapes are linguistic fossils from an earlier stage. Words for larger numbers may reveal grouping. An expression can mean 2 10s, 3 20s, or 5 groups of 12. Once repeated grouping enters language, it begins to resemble the structure of a written number system. Still, speaking a number and recording it are different problems. A spoken sequence disappears as soon as it is said. A permanent record must give quantity a lasting form. Tally marks work well when each mark represents one item. They become inefficient when communities begin managing larger herds, harvests, stores, labour forces, taxes, and exchanges. The growth of settled life increased that pressure. For most of human existence, people lived in small, mobile groups. Their possessions were limited by what they could carry, and many social relationships were direct.
A person could often remember who had given what, who had borrowed a tool, and how food was shared. As agriculture spread, the scale of organization changed. Fields produced harvests that had to be stored. Animals had to be tracked. Seed grain needed to be reserved. Some goods were collected for temples, rulers, or communal projects. Workers might receive regular rations. Exchanges could involve people who were not present at the same time. Quantity now had to survive across seasons and across distance. Memory alone was not enough. The ancient Near East provides one of the clearest records of how physical counting tools gradually became written signs. Beginning several thousand years before the first cities, people in the region used small clay tokens in different shapes. A cone might represent one measure of grain. A sphere could stand for another type or amount of goods. Other shapes represented livestock, oil, or manufactured items.
The exact interpretation of particular tokens changed across time and place, but the general system is clear. Information was being stored in objects. Suppose a farmer owed a storehouse several containers of oil. A token could be selected for each container. The group of tokens preserved the obligation. Anyone who understood the shapes could inspect them and recover the record. This method was more flexible than a simple row of scratches because different token shapes could encode different categories. Quantity and type could be represented together, yet loose tokens created practical problems. They could be lost, added, removed, or mixed with tokens from another transaction. One solution was to seal them inside a hollow clay envelope, often called a bulla. The wet clay could be marked with seals, identifying the people or institutions involved. Once the envelope hardened, the tokens inside were protected. To alter the contents, someone would have to break the container. But the protection created another inconvenience. How could anyone know what was inside without destroying the envelope? In some cases, the tokens were pressed into the outer surface before being sealed. Their impressions showed the contents. Now pause and consider the structure of that system. The actual tokens are hidden inside. Their shapes are copied onto the outside. The impressions carry the same information as the objects themselves. Once the outer marks are trusted, the inner tokens become unnecessary.
A person can press a token into a flat clay surface and keep only the impression. Later, a stylus can draw or stamp a simplified sign without using the original token at all. The record has moved from three-dimensional objects to two-dimensional marks. This transition unfolded over a long period and did not happen through one dramatic moment of invention.
Still, it leads toward one of the most important transformations in human history. Counting helped create writing. Some of the earliest surviving clay tablets from Mesopotamia are administrative records. They concern grain, livestock, labor, land, and deliveries. Long before writing carried epic poetry or personal letters, it helped institutions answer practical questions. How much was received? How much was distributed? Who owed what? How many workers were present? Numbers were deeply connected to the birth of written administration. The earliest numerical signs were not yet a single universal set of digits. Different goods could be counted with different systems. A measure of grain might use one sequence of signs, while animals or areas of land used another. This feels strange from a modern perspective. We use the same digit 7 for 7 sheep, 7 gallons, 7 days, or 7 miles. The object changes, but the number remains the same. Early systems often kept the quantity more closely tied to the thing being counted. That connection gradually loosened. A symbol that once meant a particular amount of a particular good could become a more general numerical sign. The idea of number was slowly separating from the objects. This is one of the deepest developments in the story. When a person understands 7 only as 7 sheep, the concept remains attached to sheep. When the same 7 can apply to sheep, jars, people, days, or stars, number becomes abstract. Abstraction allows mathematics to travel. A rule discovered while dividing grain can later be used for money, distance, or time. The objects no longer control the structure. The relationship between quantities becomes the main subject. In southern Mesopotamia, cities grew during the 4th millennium before the Common Era. Their administrations needed increasingly sophisticated records. Scribes developed signs impressed or drawn into clay, and these signs gradually evolved into cuneiform writing. A reed stylus pressed into wet clay produced wedge-shaped marks. The tablets could be dried and stored. Some were later baked accidentally in fires, preserving them for thousands of years. The numerical systems used by Sumerian and later Babylonian scribes were unlike our decimal notation. They drew on several earlier counting traditions, but one of their greatest achievements was a system based largely on 60. Why 60? No single explanation is certain. The system may have grown from the combination of older grouping practices, including groups of 10 and groups of 6. Finger counting may also have played a role. Whatever its origin, 60 offered practical advantages because it could be divided into many equal parts. A base tells us when a position is complete and must be carried into the next place. In our decimal system, 10 ones become 110, 10 tens become 100, 10 hundreds become 1,000. In a base 60 system, 60 units become 1 unit of the next order. The Babylonians eventually used a limited set of cuneiform signs and allowed position to determine value. One basic wedge could represent 1 unit. A different combination could represent 10. These signs were combined to form values up to 59. After that, a new position began. This was a remarkable form of compression. A sign could mean 1, 60 or 3,600 depending on where it stood. The same principle governs our own notation. The digit 5 can mean 5 ones, 5 tens, 5 hundreds, or 5 thousands. Its shape remains unchanged. Position supplies the scale. Positional notation is one of the most powerful ideas ever developed because it allows a small collection of symbols to represent values of unlimited size.
Without position, a culture needs new symbols for 10, 100, 1,000, 10,000, and every greater order. With position, the same digits can be reused. The Babylonian system was not identical to modern notation. It lacked a fully developed zero for much of its history, and this created ambiguity. Imagine seeing a pair of symbols with a space between them. Does the first belong to the next position, or has the writer simply left a gap? Is the value 1 and 1, 60 and 1, or an even larger combination? Context often resolved the problem. A tablet about land measurements, prices, or astronomy gave trained scribes clues about the expected scale. Later, Babylonian writers used a placeholder mark inside some numbers to show that a position was empty. That placeholder was an important step toward zero, but it was not yet zero as a complete number. It functioned more like punctuation. It told the reader that nothing occupied a particular place. It was generally not treated as a value that could be freely added, subtracted, or multiplied. Even with these limitations, Babylonian mathematics became highly advanced. Scribes created multiplication tables and lists of reciprocals. They solved problems equivalent to linear and quadratic equations. They worked with areas, volumes, interest, and geometric relationships. Because 60 has many divisors, common fractions could be expressed neatly. 1/2, 1/3, 1/4, 1/5, and 1/6 all fit naturally into base 60. We still carry the remains of this system. An hour contains 60 minutes. A minute contains 60 seconds. A full circle contains 360 degrees. These conventions have survived empires, languages, religions, and technologies. Every time we say that a video lasts 12 minutes, or that an angle measures 90 degrees, we are using a distant descendant of Mesopotamian calculation. One small Babylonian clay tablet, now known by a modern museum label, shows a square and its diagonal. The tablet includes a very accurate approximation of the square root of 2 expressed in base 60. The value is correct to several decimal places when converted into our notation. This tells us that Babylonian scribes could calculate with impressive precision long before Greek mathematics reached its classical form. Knowledge was not moving along one simple line from one famous thinker to the next. Different cultures developed methods suited to their own needs, and many contributors remain unnamed. While Mesopotamian scribes worked with base 60 and positional value, ancient Egypt followed another path. Egyptian numerals were decimal, meaning they grouped quantities by powers of 10. There were separate symbols for 1, 10, 100, 1,000, 10,000, 100,000, and 1,000,000. To write a number, the necessary symbols were repeated.
A value containing 3 hundreds, 4 tens, and 2 ones would use 300 signs, 4 10 signs, and 2 unit strokes. The order could vary more than it does in modern notation because each symbol carried its own value. A 100 sign meant 100 wherever it appeared. This made Egyptian numerals easy to interpret once the symbols were known. It also made large numbers lengthy to write. The system was additive. The reader added the values of all the signs. It was not fully positional. Moving a symbol did not automatically multiply it by 10. Egyptian scribes still performed sophisticated calculations. They used methods based on doubling for multiplication and worked with fractions, often expressing them as sums of unit fractions with 1 as the numerator. A fraction such as 2/3 could have its own special treatment, while many other fractions were decomposed into combinations like 1/2 plus 1/6. To a modern reader, this may look cumbersome. Within the Egyptian system, it provided a consistent method supported by tables and training. The comparison between Egypt and Mesopotamia reveals something essential. A number system is a tool shaped by the problems, materials, and institutions around it. Egyptian notation made magnitudes visible through repeated symbols. Babylonian notation compressed values through position. Each offered advantages and created difficulties. There was no single moment when humanity discovered the one correct way to write numbers. Many systems emerged. Some were carved into stone for monuments. Some were written quickly by scribes. Some were manipulated with counters on boards. Some were tied to calendars, trade, astronomy, or ritual. Centuries later, Greek communities developed several numeral systems. One approach used signs connected to the first letters of number words.
Another assigned numerical values to letters of the alphabet. In an alphabetic system, one group of letters could represent the units from 1 through 9, another group the tens, and another the hundreds. This produced fairly compact written numbers, but it required many distinct symbols. A letter representing 20 remained 20 wherever it appeared. Position did not transform it into 200 or 2000. Greek mathematicians created extraordinary geometry and number theory while working without the written arithmetic familiar to us. They often relied on counting boards for calculation and geometric diagrams for proof. The written numeral recorded a result, while the actual manipulation of quantities might happen elsewhere. The same separation later appeared in Rome. Roman numerals used signs such as I, V, X, L, C, D, and M. Their values were combined through addition and, in some cases, subtraction.
They worked well on buildings, coins, legal records, chapter headings, and public inscriptions. Their forms remain visible today. They are much less convenient for multiplication or long division. Try to multiply two large Roman numerals directly on paper. There are no aligned decimal places. There is no zero holding an empty position. The symbols do not repeat through powers of 10 in a simple way. Roman merchants and officials therefore used counting boards and forms of the abacus. Lines or columns represented different orders of value. Counters placed in one column meant units. The same counters moved to another column meant tens, hundreds, or thousands. The board was positional even when the written numerals were not. This distinction is crucial. People understood the usefulness of place value physically before written symbols fully captured it. A counter has no permanent value of its own. Its location gives it meaning. Moving it one column changes its scale. When enough counters accumulate in one place, they can be exchanged for one counter in the next place. This is the ancestor of carrying during addition. If a higher place is empty, a counter can be borrowed and converted into units of the lower place. This is the physical ancestor of borrowing during subtraction. Modern written arithmetic hides these actions inside marks on paper, but the logic was practiced with objects for centuries. China developed an especially powerful tradition using counting rods. Small rods were arranged on a flat surface in positions representing units, tens, hundreds, thousands, and beyond. Their orientation changed from one position to the next, helping the eye separate adjacent places. The rods could be moved during calculation. A mathematician could add, subtract, multiply, divide, extract roots, and solve systems of equations by rearranging them.
The written record and the calculating device were closely connected, but empty positions still presented a problem. On a board, an empty column can show that no tens or no hundreds are present. On a written page, empty space can shrink, expand, or disappear. Once again, positional thinking created a demand for a visible sign of absence. Chinese mathematicians also used rods to represent positive and negative quantities, a development we will return to much later. Their willingness to treat debts and opposing values as objects of calculation moved them beyond many other traditions. Across the ocean, the Maya created another highly developed number system independently. It was largely based on 20. Dots represented units, and bars represented groups of 5. Numbers were arranged vertically in positions of increasing value. The Maya also used a shell-like sign for an empty position. This sign played an important role in calendar calculations, where a missing place could completely change a date. The Babylonian placeholder and the Mayan zero sign show that position repeatedly creates the same problem. When value depends on place, absence must somehow be recorded. Yet a placeholder alone does not produce the full arithmetic of 0. A blank position says that no units of a certain order are present. A number called 0 must do more. It must represent the result when all quantity has been removed. It must stand at the boundary between positive and negative values. It must take part in rules of calculation. That next step would emerge most fully in India. Before we reach it, however, consider how far the idea of number has already traveled. It began with direct comparison. One person matched with one pebble. One animal matched with one mark. The mark then became part of a group. Groups became units of larger groups. Different symbols represented different scales. Finally, position allowed the same symbol to carry many values. Every stage solved a problem created by the one before it. One-to-one matching preserved a small quantity, but became inconvenient for large records. Tallies stored information, but became too long. Grouping compressed the marks, but required shared rules. Special symbols shortened the record, but demanded many signs. Position reused a small set of signs, but created dangerous empty places. By this stage, number had become far more than a way to remember a flock. It could organize a city, divide land, schedule labor, compare harvests, calculate payments, and trace the movements of the sky. Yet all of these achievements still depended on systems that were incomplete in different ways. Some could record large values but made calculations slow. Some supported calculation but depended on a physical board. Some used position but left empty places uncertain. Some represented absence in a calendar, without treating absence as a quantity. The next breakthrough would bring several of these ideas together. It would combine decimal grouping, positional value, written calculation, and a visible mark for an empty place. Once those pieces were joined, arithmetic could be carried across a page by repeatable rules. A person would no longer need a different symbol for every new scale, and the written number itself could guide the calculation. Now the entire system was waiting for a symbol that could hold nothing without allowing the structure to collapse. The invention of that symbol would seem simple after it became familiar. At the time, it required people to accept a difficult idea. How can nothing be written? How can absence occupy a place? And once absence has a sign, can it become a number in its own right? The answer would change arithmetic forever. It would also open the door to a new and unsettling possibility. Because the moment 0 becomes a point on the number line, mathematics can begin asking, what lies on the other side? People often imagine that once humans learned how to count,
The story of numbers was almost complete. In reality, counting was only the beginning. The first tally marks solved a simple problem. They helped people remember quantities that were too important to trust to memory alone. Small groups became larger communities. Villages became cities. Trade expanded across rivers, deserts, and seas. Every new step created questions that older counting methods could no longer answer. A shepherd could remember a small flock. A farmer could remember a few baskets of grain. But kingdoms could not rely on memory. The larger society became, the more information had to survive long after the people who created it were gone. This changed the purpose of numbers.
They were no longer used only to count objects. They became tools for organizing civilization. Imagine arriving at a busy marketplace in ancient Mesopotamia. Merchants are exchanging grain, wool, oil, copper, and pottery. Some goods arrive today, others will arrive next month. Some belong to temples, others belong to private families. Taxes must be collected, workers must be paid, storehouses must be inspected. None of this can function for very long without reliable records. Every transaction raises the same questions. How much arrived? How much left? Who owns it? Who owes it? Who has already paid? At this point, numbers stop being a convenience. They become part of the foundation of government. As cities continued to grow, record-keeping became one of the most respected professions. Scribes spent years learning how to write. They copied documents, recorded harvests, measured fields, calculated wages,
Tracked livestock, maintained inventories. Their work depended on numerical systems that were becoming more sophisticated with every generation. One remarkable feature of these early systems is that they were practical long before they became elegant. People were interested in solving real problems. They needed methods that worked. Beauty came later. For example, imagine measuring a field after the Nile flooded its banks. The old boundaries have disappeared. Stones marking the corners have been washed away. The land must be measured again before taxes can be collected. Without consistent numerical methods, disputes become unavoidable. One farmer believes his field has become smaller. Another insists it has become larger. Numbers become a neutral language that both sides can examine. The same thing happens in construction. A temple cannot be built if every worker measures differently. A canal cannot reach its destination if distances change from one surveyor to another. Large societies require standard measurement just as much as they require standard counting. Gradually, numbers become connected with length, weight, volume, area, and time. They begin describing the world itself. Astronomy pushed numerical thinking even further. Long before telescopes existed, careful observers noticed repeating cycles in the sky. The sun followed a predictable path. The moon changed its appearance in regular stages. Certain stars returned to the same positions year after year. These patterns encouraged people to record observations over long periods. Without numbers, such records quickly became impossible. Astronomy and mathematics grew together because each depended on the other. Predicting eclipses required calculation. Creating calendars required counting. Planning agriculture depended on those calendars. A successful harvest often depended on understanding time. Slowly, numbers expanded beyond simple collections of objects. They became descriptions of change. They measured motion. They measured seasons. They measured the passing of life itself.
Yet despite all these advances, something important was still missing. Positional systems had become extraordinarily powerful. The same symbol could represent different values depending on where it appeared. That efficiency transformed arithmetic, but it also created a dangerous weakness. How should a writer represent an empty position? Imagine writing a value with no tens but several hundreds. If nothing marks the missing place, readers may misunderstand the entire number. At first, different civilizations solved this problem in different ways. Some relied on spacing, some relied on context, some created placeholder symbols.
These solutions worked surprisingly well for experienced scribes. But they did not completely solve the deeper problem. A placeholder is not yet a number. It merely protects the structure of other numbers. The next breakthrough would require a much bolder idea. Someone would eventually ask a question that sounds almost childish. Can nothing itself become something that we write? That question would transform mathematics forever. The idea of writing nothing may sound obvious today. Every child learns that 0 is part of the counting sequence almost as soon as they learn the other digits. But for most of human history, nothing was not treated like an ordinary number. If a basket contained apples, it could be counted. If a field produced grain, it could be measured. If a merchant owned livestock, every animal could be recorded. When nothing was present, many people simply wrote nothing at all.
That habit worked surprisingly well until positional notation became more common. Once the value of a symbol depended on its location, silence became dangerous. Imagine reading a record hundreds or even thousands of years after it was written. A small gap in the text could be accidental. A piece of clay might have broken away. A careless scribe might have left extra space. Without a visible sign, nobody could be completely certain whether a place was intentionally empty or simply missing. Babylonian scribes eventually introduced placeholder marks inside certain numbers. The Maya independently created their own symbol for an empty position while building their remarkable calendar system. Both traditions recognized the same practical problem. An empty place needed to be protected. Yet neither tradition fully transformed that empty place into a number that could stand on its own. That final step would happen in India.
By the early centuries of the Common Era, Indian mathematicians were already working with sophisticated positional decimal notation. Unlike many earlier systems, this notation used only a small collection of symbols whose values changed according to position. The structure was elegant, it was efficient, it made calculation dramatically easier. Still, one question remained. How should an empty place be represented? The answer gradually appeared as a small circular symbol. At first, it functioned exactly as a placeholder, but over time something remarkable happened. The symbol itself began to acquire meaning. It no longer represented only an empty position inside another number. It represented the quantity of nothing. This sounds simple only because we have grown up with the idea. Philosophically, it was astonishing. How can nothing be written? How can nothing participate in arithmetic? How can something that represents the absence of quantity become part of mathematics itself? These questions challenged centuries of intuition. One of the greatest figures in this story was the Indian mathematician Brahmagupta. In the 7th century, he described rules involving 0 with a level of clarity that had never existed before. He explained how positive and negative numbers interact with 0. He described what happens when 0 is added to another number or subtracted from it. Not every conclusion matched modern mathematics, especially when division by 0 was involved, but the conceptual leap had already been made. 0 was no longer merely protecting the position of other digits. It had become a mathematical object. Once that happened, arithmetic changed forever. Imagine trying to multiply large numbers without positional notation and 0. The work becomes slow and repetitive. Now imagine writing the same calculation using the decimal place value system. Columns align naturally. Carrying values becomes systematic. Large calculations that once demanded enormous effort become almost routine. This efficiency spread gradually through trade, scholarship, and translation. Indian mathematical works influenced scholars writing in Arabic. Centuries later, those ideas entered Europe through translations and commercial practice. At first, many people resisted the unfamiliar symbols. Roman numerals had been used for generations. Merchants trusted the methods they already knew. Some authorities even worried that the new numerals might be altered too easily. Changing one small mark could transform the value of a record. Despite this resistance, the practical advantages were impossible to ignore. Bookkeeping became easier, calculation became faster, astronomy became more accurate, engineering benefited, commerce expanded. The decimal positional system slowly became the dominant language of arithmetic. Today, we rarely stop to appreciate how extraordinary it really is. With only 10 symbols, every whole number can be written. The same symbols describe populations, microscopic particles, distances between galaxies, and the amount of money in a bank account. The system is compact, flexible, and remarkably powerful. Most people never wonder why it works so well because they have never known anything else. But history reminds us that it could have developed very differently. Humanity experimented with many numerical languages before settling on the one most of the world now shares. And even after zero finally found its place, the story of numbers was still far from complete. A far stranger challenge was already waiting. What happens when subtraction pushes us below zero? Can a debt become a number just as real as a possession?
Many mathematicians believed the answer had to be no. History would prove otherwise. For centuries, zero slowly earned its place in mathematics. Its journey was anything but easy. Many scholars accepted it because it made calculation easier, not because they fully embraced the idea behind it. History often works this way. A useful idea is adopted first. Its deeper meaning is understood much later. As merchants, astronomers, architects, and engineers continued using positional notation, the advantages became impossible to ignore. Large calculations that once required tables, counting boards, or specially trained scribes could now be performed directly on paper. Mathematics became faster, more reliable, more portable. Knowledge that once depended on years of specialized training slowly became accessible to a much larger community. This change helped transform commerce throughout Asia, the Middle East, and eventually Europe.
A merchant could compare prices more quickly. An architect could estimate materials with greater confidence. An astronomer could calculate planetary positions with improved accuracy. The decimal system did not simply make mathematics easier, it accelerated civilization itself. Yet every solution creates another question. Once zero became part of arithmetic, subtraction acquired a new kind of freedom. Imagine beginning with 5 apples. Remove one, then another. Eventually, none remain. Until recently, the calculation would simply stop. There was nothing left to count. But mathematics now had a symbol for that empty quantity. Zero had become a destination. Then someone asked the obvious next question. What happens if one more apple must still be removed? In everyday life, the question sounds impossible. You cannot take an apple that is no longer there. In trade, however, the situation appears constantly. A merchant may owe grain that has not yet been delivered. A farmer may borrow seed for next year's harvest. A government may spend resources before collecting taxes. These situations are real. The quantities involved are real, yet ordinary counting cannot describe them. The story of numbers was about to expand once again. A quantity that seemed impossible would slowly become one of the most useful ideas in mathematics. The next chapter begins with something almost everyone has experienced at least once: debt. For thousands of years, people understood debt perfectly well. Accepting it as a number would take much longer. If there is one idea that feels perfectly natural today, it is that every number has another number on the other side of zero. Positive, zero, negative. We see temperatures below zero on weather forecasts. We see negative balances in financial reports. Engineers, scientists, and programmers work with negative values every day. It is difficult to imagine mathematics without them. For most of history, however, negative numbers seemed impossible. People understood debt. They understood loss. They understood the difference between owning something and owing something. What they did not understand was how a quantity smaller than nothing could be treated as a real number. The hesitation was understandable. Imagine asking an ancient merchant how many sheep he owned. You might answer 20, or 10, or none. But how could he possibly own -5 sheep? The question sounds absurd because sheep are physical objects. You cannot place fewer than none inside a field. The problem was not arithmetic. It was interpretation. Throughout history, numbers were closely tied to real objects. When numbers described grain, animals, coins, or pieces of land,
Negative quantities seem to have no physical meaning. Yet trade slowly revealed a different picture. Imagine borrowing 100 silver coins to finance a trading expedition. You leave with money that is not truly yours. Your account does not contain wealth. It contains an obligation. That obligation is just as real as the coins themselves. If another merchant examines your finances, the debt cannot simply be ignored. It changes your true position. For practical accounting, a debt behaves like a quantity opposite to wealth. This simple observation became one of the great turning points in mathematical history. Instead of asking how someone could own negative sheep, mathematicians began asking a different question. Can numbers represent relationships instead of objects? That change in perspective opened an entirely new world. Ancient Chinese mathematicians were among the earliest to treat positive
and negative quantities systematically. Using counting rods placed on a counting board, they represented gains and losses with different colors or orientations. Positive quantities and debts could be manipulated according to clear computational rules. For them, the distinction was practical rather than philosophical. Merchants dealt with profits and losses every day. Administrators balanced accounts. The mathematics reflected reality. In India, Brahmagupta expanded these ideas even further. He described rules for combining positive numbers, negative numbers, and zero. Many of the relationships taught in classrooms today can already be recognized in his work. A debt added to another debt becomes a larger debt. A fortune added to another fortune becomes a greater fortune. When a fortune cancels a debt, the result depends on which quantity is larger. These ideas sound almost obvious now. They were anything but obvious at the time. Europe accepted negative numbers much more slowly. Many mathematicians called them absurd, false, or impossible. Even when calculations produced negative answers, some scholars simply rejected those solutions. Others described them as meaningless. The resistance lasted for centuries. Part of the difficulty came from geometry. A length cannot be negative. The side of a square cannot measure less than nothing. Since geometry played such a central role in mathematics, many thinkers struggled to accept quantities that could not be drawn directly. The breakthrough arrived gradually. Instead of viewing numbers as measurements alone, mathematicians began thinking of them as positions. Imagine standing on a straight road. Choose one point as the starting position. Walking east moves you in one direction. Walking west moves you in the opposite direction. Neither direction is more real than the other. The starting point naturally becomes 0.
Positions to one side become positive. Positions to the other become negative. For the first time, every integer found a natural home. The number line did something extraordinary. It transformed arithmetic into movement. Adding became walking forward. Subtracting became walking backward. Negative numbers were no longer mysterious objects. They were locations. This picture made many old rules easier to understand. Subtracting a positive value means moving left. Subtracting a negative value means removing movement to the left. The result is movement to the right. Rules that once seemed arbitrary suddenly acquired geometric meaning. Even multiplication began to reveal patterns. Repeated addition explains why positive times positive remains positive. Repeated movement in the opposite direction helps explain why a negative multiplied by a positive remains negative. The final rule, negative multiplied by negative, puzzled mathematicians for centuries. Eventually, they realized that preserving the internal consistency of arithmetic required the product to become positive. Without that rule, many familiar patterns would collapse. Mathematics was expanding once again. Each new type of number preserved the old rules while extending them into a larger world. Natural numbers solved counting. 0 represented absence. Negative numbers represented opposition. Yet another problem was already waiting. Imagine drawing the simplest possible square. Each side measures exactly 1 unit. Now measure the diagonal. No matter how carefully you calculate, no fraction will ever describe it exactly. The next crisis would not emerge from trade. It would emerge from geometry itself. And it would force humanity to discover numbers that never repeat, never end, and can never be written as a simple ratio.
For centuries, geometry had been considered the most certain branch of mathematics. A line could be drawn, a triangle could be measured, a square could be constructed with remarkable precision. Unlike trade or accounting, geometry seemed to describe permanent truths about the physical world. That confidence would soon be challenged by one of the simplest figures imaginable. Draw a perfect square. Let each side measure exactly 1 unit. Now draw a line connecting opposite corners. This new line, the diagonal, appears completely ordinary. Nothing about it suggests mystery. The ancient Greeks knew a theorem that allowed its length to be calculated. Today we call it the Pythagorean theorem. The square built on the diagonal must equal the combined areas of the squares built on the 2 sides. For a square whose sides each measure 1 unit, the diagonal has a length equal to the square root of 2. The calculation itself is straightforward. The problem comes afterward. What kind of number is the square root of 2? The Pythagoreans believed that every measurable quantity could ultimately be expressed as the ratio of 2 whole numbers. In other words, every length should be representable as a fraction. The universe appeared orderly because ratios seemed to govern everything from music to geometry. Then came an unsettling discovery. No matter which fraction was tested, none matched the diagonal exactly. People searched for larger numerators, larger denominators, better approximations. The fractions grew closer and closer, but they never became exact. Eventually, mathematicians proved that no fraction could ever equal the square root of 2. The diagonal refused to fit inside the numerical world they believed was complete. Later generations called such quantities irrational numbers. The word does not mean unreasonable or illogical.
It simply means that the value cannot be written as a ratio of two integers.
Its decimal expansion never ends. It never settles into a repeating pattern. You can calculate more digits forever without ever reaching the end. The discovery shook Greek mathematics. According to later tradition, the result was so disturbing that it was kept secret within the Pythagorean community. Stories claim that Hippasus, who was associated with the discovery, was punished after revealing it. Whether the legend is historically accurate remains uncertain. What matters is that the discovery itself was real. Mathematics had uncovered a quantity that could not be described using fractions. The crisis forced mathematicians to rethink the meaning of number. For a long time, geometry became the safest place to work with these new quantities. Instead of treating them as ordinary numbers, many Greek mathematicians represented them as lengths.
A line segment could exist even if no fraction described it exactly. Geometry provided certainty where arithmetic still struggled. Centuries later, these irrational quantities would become fully accepted as numbers in their own right. Today, they appear everywhere. The square root of 2 describes diagonals. Pi appears whenever circles are involved. The number e governs growth, decay, and compound interest. Modern science depends on irrational numbers so completely that removing them would make much of physics impossible. History repeated its familiar pattern. A new problem appeared. Existing numbers could not solve it. Mathematics expanded. The old system survived inside a larger one, and almost immediately, another challenge emerged. Algebra would soon produce expressions that seemed even more impossible than irrational numbers. This time, the mystery would not come from geometry. It would come from trying to solve equations.
By now, the pattern should feel familiar. Every expansion of the number system began with a problem that older numbers could not solve. Whole numbers could count. Fractions could describe parts of a whole. 0 represented absence. Negative numbers represented direction and debt. Irrational numbers captured lengths that no fraction could express. Each discovery seemed shocking at first. Each eventually became indispensable. Many mathematicians believed that irrational numbers might be the final great expansion. They were wrong. The next challenge emerged from algebra. Unlike geometry, algebra did not begin with shapes. It began with unknown quantities. Instead of asking how long a line might be, algebra asked what value would satisfy an equation. For simple equations, the answers were familiar. As algebra matured, mathematicians searched for general methods that could solve increasingly difficult problems.
The competition was especially intense during the Renaissance. Italian mathematicians challenged one another publicly. A successful method could bring enormous prestige. Keeping a new technique secret offered a powerful advantage. Eventually, methods for solving cubic equations began to appear. One of the most important names in this story is Girolamo Cardano. His famous book, Ars Magna, gathered together several breakthroughs in algebra and helped spread them throughout Europe. While working through certain cubic equations, something deeply unsettling happened. The final answer was perfectly ordinary, yet the calculation seemed to pass through an impossible intermediate step. Expressions appeared that required taking the square root of a negative quantity. No known number could satisfy such an operation. Every positive number becomes positive when multiplied by itself. Every negative number also becomes positive when multiplied by itself. Nothing seemed capable of producing a negative square. Many mathematicians wanted to ignore these strange expressions entirely. They appeared meaningless, and yet the equations worked.
If the impossible quantities were carried through the calculation instead of being discarded, the correct, real answer often emerged at the end. It was an extraordinary situation. An apparently impossible object was helping produce perfectly correct results. The Italian mathematician Raphael Bombelli decided not to avoid these expressions. Instead, he asked a bold question. What if these mysterious quantities obey consistent rules of their own? Rather than treating them as mistakes, he explored how they interacted during calculation. His work laid the foundations for what would later become complex numbers. The full meaning of these numbers would not become clear for generations. Many scholars continued calling them imaginary. The name survived, although it can be misleading. Imaginary numbers are not imaginary in the ordinary sense of the word. They are logical mathematical objects that obey precise rules and describe many real physical systems. Just as negative numbers once seemed absurd, these new numbers slowly earned acceptance through usefulness. Electricity, wave motion, signal processing, quantum mechanics. Modern engineering relies on complex numbers every day. History repeated itself once more. The impossible became practical, the unimaginable became ordinary, and mathematics grew larger without abandoning anything that had come before. The natural numbers still existed, fractions still worked, negative values remained essential. Irrational numbers still describe geometry. The new system simply contained all of them inside a broader mathematical universe. But one final mystery still remained.
If numbers could continue expanding almost without limit, what exactly was infinity? Was it merely an idea? Or could infinity itself become something mathematics could compare, classify, and understand? That question would transform mathematics more dramatically than anyone expected. Imagine trying to write a very large number without using the digit 0. Not pronounce it, not think about it. Actually write it down. Try to record 1,000, or 10,000, or 1,000,000. Suddenly, something that feels effortless today becomes strangely complicated. Without 0, entire places inside a number simply disappear. There is no simple way to distinguish 100 from 10, or 1,000 from 1. The difference between these values depends on something that appears to represent nothing at all. It is easy to overlook how extraordinary this idea truly is.
From most of human history, people had learned to count, measure, trade, build cities, predict eclipses, and even develop sophisticated mathematics without possessing a genuine number for nothing. That absence did not seem like a problem at first. Early number systems were designed for practical tasks. Farmers counted livestock. Merchants counted sacks of grain. Builders counted stones. Priests counted days. Every number represented something that physically existed. If there was nothing to count, there was simply nothing to record. The absence of objects did not require its own symbol. Why invent a number for an empty basket? An empty basket was simply empty. This way of thinking survived for thousands of years. The earliest civilizations had remarkably sophisticated mathematics, despite lacking what we now consider one of its most essential building blocks.
Egyptian scribes could calculate taxes, divide harvests, and design monuments whose precision still amazes engineers today. Babylonian astronomers predicted celestial events with astonishing accuracy. Neither civilization possessed the modern concept of 0. Their mathematics functioned because their number systems had evolved around the problems they actually needed to solve. As societies became larger, however, numbers themselves began changing. In small villages, people rarely needed to distinguish between 10,000 and 100,000. But cities transformed everything. Governments collected taxes from thousands of citizens. Merchants tracked enormous inventories. Empires counted soldiers, fields, buildings, and shipments traveling across hundreds of miles. Numbers became larger, much larger. And with larger numbers came a new problem: not calculating them, writing them. Imagine a merchant recording 302 jars of oil. Now imagine another shipment containing only 32 jars. If the writing system cannot clearly indicate the missing tens or hundreds, confusion becomes inevitable. A single missing symbol can completely change the meaning of a record. What appears to be a tiny gap suddenly carries enormous importance. This challenge became especially significant in Mesopotamia. The Babylonians possessed one of the most advanced mathematical systems of the ancient world. Unlike the decimal system familiar today, they used a positional system based on 60. At first glance, this seems unusual. Why 60? Why not 10 or 20? The answer probably lies in practicality. 60 is an exceptionally convenient number. It can be divided evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. Very few numbers have so many divisors. For merchants dividing goods or astronomers dividing circles, this flexibility proved extremely useful. Even today, traces of Babylonian mathematics remain woven into everyday life. An hour contains 60 minutes. A minute contains 60 seconds. A circle contains 360 degrees. Every time we check a clock, we unknowingly use an inheritance from ancient Babylon. Their positional notation represented a remarkable breakthrough. Instead of inventing new symbols for every larger value, the position of a symbol determined its meaning. A single mark could represent 1, or 60, or 3,600. Its location determined its value. This idea was revolutionary. It dramatically simplified writing enormous numbers. Yet it introduced a completely unexpected problem. Suppose a scribe wished to record one value, then another value that contained an empty position. How should that empty position be shown? Leaving a blank space seemed obvious. Unfortunately, blank spaces are unreliable. Writing styles differ. Clay tablets become damaged, cracks appear, edges crumble. A narrow gap might be intentional or accidental. Future readers could not always tell. Imagine opening an old handwritten book centuries from now. A tiny smudge separates two words. Was the space always there? Did the ink fade? Did part of the page disappear? Small uncertainties quickly become major misunderstandings. Babylonian scribes eventually developed a clever solution. Rather than inventing a true number for nothing, they created a special placeholder. This symbol announced that a position existed, but currently contained no value. It functioned much like an empty seat reserved in a theater. The seat itself mattered. Someone could potentially occupy it. Its existence helped everyone understand the arrangement of the rows. But an empty chair is not the same thing as the number 0. The Babylonian placeholder solved a writing problem. It did not solve a mathematical one. No one treated this symbol as an ordinary number. It could not be added, subtracted, multiplied, or divided. It merely prevented confusion. Even so, this small innovation represented a profound conceptual shift. For perhaps the first time, nothing acquired a visible presence. Absence itself received a mark. Not because philosophers demanded it, not because mathematicians sought elegance, because accountants hated ambiguity. Again and again throughout history, mathematics advanced for surprisingly practical reasons. Trade demanded better arithmetic. Construction demanded better geometry.
Navigation demanded better astronomy. Now administration demanded a better way to describe empty positions inside numbers. Ideas that later transformed philosophy often began as solutions to ordinary bookkeeping. Meanwhile, on the opposite side of the world, another civilization followed a remarkably different path.
Across the forests and cities of Mesoamerica, the Maya developed one of the most sophisticated mathematical traditions in the ancient Americas. Like the Babylonians, they also created a positional number system. Unlike the Babylonians, however, their system was primarily based on 20. Historians believe this choice probably reflected the human body itself. 10 fingers, 10 toes, 20 digits altogether. Counting with both hands and feet naturally encouraged a base 20 structure. The Maya became extraordinary astronomers. They tracked the movements of the sun, moon, and planets with impressive precision. Their calendars coordinated agricultural cycles, ceremonies, and political events across generations. Such work required enormous numerical accuracy. And accuracy required a clear positional system. To represent an empty place, Maya scribes developed a distinctive shell-shaped symbol. Modern readers often describe it as a zero.
That description is broadly correct, but it requires careful qualification. The Maya symbol functioned within their positional notation and calendar calculations in ways strikingly similar to zero. It marked the absence of a value in a specific position. Without it, many calculations would have become hopelessly confusing. Yet the Maya concept developed independently from the one that would later emerge in India. These were not ideas spreading across a connected world. They were separate civilizations confronting remarkably similar problems. Again, necessity drove invention. Whenever positional notation matured, the same challenge appeared. How do you write nothing without saying nothing? How do you preserve an empty place? How do you distinguish between absence and omission? Civilizations separated by oceans arrived at surprisingly similar answers. This convergence tells us something important about mathematics.
Many discoveries do not happen because one culture teaches another.
Sometimes, different societies independently encounter the same logical obstacle. Presented with identical problems, human minds often discover remarkably similar solutions. Yet, despite these impressive achievements, something fundamental still remained missing. Neither the Babylonian placeholder nor the Maya shell symbol had fully transformed nothing into a genuine number. They described empty positions. They organized notation. They simplified calculation. But almost no one yet asked the deeper question. Can nothing itself be counted? Can nothing participate in arithmetic? Can nothing become something mathematics can manipulate just like any other number? At first, the question sounds almost ridiculous. How can nothing become something? How can absence possess its own identity? The difficulty was not mathematical, it was philosophical.
Ancient thinkers across many civilizations struggled with the very concept of nothingness. Greek philosophers debated whether empty space could truly exist. Some argued that nature abhorred a vacuum. Others insisted that complete nothingness was impossible. If absolutely nothing existed somewhere, could that place even be said to exist? The conversation stretched far beyond mathematics. It reached into metaphysics, physics, and theology. Nothingness was unsettling. People naturally understand objects. They understand change. They understand motion. Nothingness, however, resists intuition. Try to imagine absolutely nothing, not darkness. Darkness is something. Not empty space. Space is something. Remove every particle, every ray of light, every sound, every direction. Even then, your mind struggles. Human imagination seems almost incapable of grasping true nothingness. Perhaps that is why civilizations hesitated for so long before granting nothing its own symbol.
Doing so required more than inventing a new mark.
It required accepting that absence itself could be treated as an object of thought. The greatest breakthrough was still waiting. It would not arrive in Babylon, nor among the Maya. It would emerge in India, where mathematicians would take a step that forever changed the history of numbers. For the first time, nothing would cease to be merely an empty place. It would become a number in its own right. India in the first millennium was unlike any other mathematical center of the ancient world. Trade routes connected kingdoms across vast distances. Merchants carried spices, textiles, precious stones, metals, and ideas. Universities attracted scholars from across Asia. Astronomy flourished. Religious calendars demanded increasingly precise calculations. Taxes had to be collected. Land had to be measured. The practical need for reliable arithmetic grew stronger with every generation.
By this time, positional notation had already demonstrated its extraordinary power. Instead of memorizing hundreds of unique symbols, a small collection of digits could represent numbers of almost unlimited size. The principle was elegant. Each position represented a different power of the base. Move one place to the left, and the value increased dramatically. Move one place to the right, and it decreased. It was an astonishingly efficient system. Yet one weakness remained. An empty position still needed to be identified. Babylonian scribes had solved that problem with a placeholder. The Maya had developed their own symbol independently. But Indian mathematicians gradually began seeing something deeper. Perhaps the empty place itself deserved recognition. Not merely as a space, not merely as punctuation, but as an actual mathematical object. The Sanskrit word they used was shunya. It is commonly translated as empty, void, or nothing.
The word already existed in philosophy, long before it entered mathematics. Many Indian philosophical traditions had spent centuries exploring ideas of emptiness, absence, and impermanence. Although mathematics and philosophy remained separate disciplines, the cultural familiarity with abstract concepts may have made the leap slightly less intimidating. Instead of asking whether nothing existed, mathematicians asked a more practical question. What happens if nothing participates in arithmetic? Imagine a merchant who owns 5 bags of grain. If he gives away all 5 bags, how many remain? Nothing. That answer had always existed in ordinary language. Now the absence itself could be written with its own symbol. Instead of leaving the page blank, the calculation ended with a mark, a symbol, a number. It seems almost trivial today. Yet this was one of the boldest conceptual shifts in the history of mathematics.
For the first time, nothing stopped being merely the absence of something else. It became an entity that could participate in calculation. This transformation reached its clearest expression in the work of the 7th century mathematician Brahmagupta. Living in Western India, Brahmagupta wrote one of the most influential mathematical works of the ancient world. His treatise covered astronomy, geometry, arithmetic, and algebra. Among its many innovations appeared something remarkably familiar: rules for calculating with zero. Today, children learn these relationships during their first years of school. At the time, they represented an intellectual revolution. Brahmagupta explained that adding zero to a number leaves the number unchanged. Subtracting zero also leaves it unchanged. If equal quantities are removed from one another, the result becomes zero.
Concepts that now appear obvious had to be stated explicitly, because humanity had never before treated zero as a genuine participant in arithmetic. Each rule strengthened the idea that zero belonged alongside every other number.
the system became beautifully consistent. Positive numbers interacted with one another. Negative numbers, already beginning to emerge in Indian mathematics, followed their own rules, and zero occupied the boundary between them. Instead of being outside mathematics, it became one of its central pillars. This consistency mattered enormously. Mathematicians value systems that behave predictably. When new ideas preserve older rules instead of breaking them, confidence grows. Zero did exactly that. Rather than complicating arithmetic, it simplified it. Calculations became cleaner. Patterns became easier to recognize. Algorithms became more reliable. Entire methods of computation suddenly became practical.
Imagine trying to multiply very large numbers without zero, or performing long division, or calculating astronomical tables containing thousands of entries. Each task becomes dramatically more difficult. Zero acts almost like invisible architecture. Most of the time we hardly notice it. Yet remove it, and the entire structure begins to collapse. One particularly important application appeared in astronomy. Indian astronomers tracked planetary motions with increasing sophistication. Even tiny numerical errors accumulated over years of observation. Accurate positional notation reduced mistakes and allowed enormous calculations to remain manageable. The heavens demanded precision. Zero helped provide it. Of course, not every question found an immediate answer. One problem proved especially troublesome. What happens when a number is divided by zero? Addition seemed straightforward. Subtraction behaved logically. Multiplication also fit naturally into the new framework. Division, however, resisted every attempt at simplification. Suppose someone owns 10 apples. Dividing them between 2 people gives each person 5. Divide them among 5 people, and each receives 2. As the number of people grows larger, each share becomes smaller. What if the number of people became infinitely large? The shares would seem to approach nothing. Now ask a different question. What happens if 10 apples are divided among 0 people? The situation no longer makes physical sense. There is no operation to perform. No sharing can occur because there are no recipients. Brahmagupta proposed rules that reflected the mathematical understanding of his time, but later generations discovered that division by zero behaves in ways far stranger than anyone had imagined. Centuries of mathematicians would wrestle with this puzzle. Even today, calculators simply display an error.
The problem remains, not because mathematics is incomplete, but because division by zero cannot be defined consistently while preserving the ordinary rules of arithmetic. Interestingly, this limitation highlights the strength of mathematics rather than its weakness. Mathematicians are willing to admit when an operation cannot be made logically consistent. Instead of forcing an answer, they preserve the integrity of the entire system. Zero had entered mathematics as a triumph, yet it also revealed new mysteries waiting to be explored. Perhaps even more remarkable than the rules themselves was how naturally they fit into the growing structure of mathematics. Zero was not an exception. It was not a special trick. It became the reference point around which the entire number system organized itself. Positive values extended in one direction, negative values extended in the other. Place value revolved around it. Algebra depended on it. Equations often sought it.
Functions crossed it. Coordinates centered upon it. Without zero, the mathematical landscape loses its center of gravity. Today, it is difficult to imagine science without that single symbol. Computers communicate through billions of zeros and ones. Engineering calculations depend upon positional notation. Bank accounts, digital storage, physics simulations, satellite navigation, and artificial intelligence all rely upon arithmetic whose foundation includes zero. Every smartphone performs countless calculations involving zeros every second. The symbol itself is tiny. Its consequences are enormous. Yet despite its elegance, zero did not immediately conquer the world. Ideas rarely spread as quickly as modern inventions. There was no internet, no printing press, no instant communication between civilizations. Knowledge traveled at the speed of caravans and ships. It crossed mountains, deserts, and oceans, carried by merchants, scholars, pilgrims, and diplomats.
The greatest journey of zero had only just begun. Before it could transform Europe, it would first travel westward through the Islamic world, where a remarkable generation of scholars would recognize its extraordinary power and preserve it for future civilizations. Ideas rarely transform the world overnight. Even the greatest discoveries often spend centuries traveling from one civilization to another. Zero was no exception. The symbol that had taken shape in India still needed to cross continents before it could become the foundation of global mathematics. That journey began along the trade routes connecting India with Persia and the rapidly expanding Islamic world. Merchants carried spices, silk, paper, metals, and precious stones. Alongside those goods traveled manuscripts, astronomical tables, metals, and precious stones. Alongside those goods traveled manuscripts, astronomical tables, engineering techniques, and mathematical ideas. Knowledge moved slowly, but it moved constantly. By the 8th century, Baghdad had become one of the greatest intellectual centers on earth. The Abbasid Caliphate stretched across enormous territories, linking cultures that had once developed largely in isolation. Greek philosophy, Persian astronomy, Indian mathematics, and countless local traditions met within the same scholarly community. Rather than simply preserving earlier knowledge, scholars translated, compared, corrected, and expanded it. One institution became legendary: the House of Wisdom. Although historians continue to debate exactly how it was organized, there is little doubt that Baghdad became a remarkable center for scientific learning. Texts arrived from many regions of the known world. Teams of translators worked to preserve them in Arabic. Astronomers refined planetary models. Physicians studied anatomy and medicine. Engineers designed machines. Mathematicians explored entirely new methods of calculation. Among the scholars associated with this intellectual movement was a man whose influence still echoes every time someone uses a computer: Muhammad ibn Musa al-Khwarizmi. Today his name is unfamiliar to many people. Ironically, almost everyone uses a word derived from it every single day: algorithm. The modern word evolved from the Latinized form of his name. Every search engine, every navigation system, every recommendation on a streaming platform, every smartphone application, every computer program ultimately relies on algorithms. The connection between this 9th century scholar and modern technology is one of history's most remarkable linguistic legacies. Al-Khwarizmi studied Indian mathematical methods with great care. He recognized something many others had not yet fully appreciated. The decimal positional system was dramatically more efficient than older numeral systems. Instead of relying on hundreds of symbols or complicated combinations of letters, calculations could be performed using only 10 digits. One of those digits represented nothing, yet without it, the remaining 9 lost much of their power. His writings explained these methods so clearly that they gradually spread throughout the Islamic world. Astronomers adopted them. Merchants embraced them. Government administrators discovered that accounting became faster and more reliable. The practical advantages were impossible to ignore. Imagine multiplying 2 enormous numbers using Roman numerals. Now imagine performing the same calculation with the Hindu-Arabic numeral system. The difference is astonishing. The newer notation was not merely easier, it changed what calculations were realistically possible.
Tasks that once consumed hours could often be completed in minutes. Errors became easier to detect. Patterns became easier to recognize.
Mathematics itself became more accessible. This practical superiority proved far more persuasive than philosophical debate. People rarely abandon familiar habits because they are told something is theoretically better. They change when daily work becomes noticeably easier. That is exactly what happened. Merchants cared about balancing accounts. Astronomers cared about predicting eclipses. Tax collectors cared about accurate records. Engineers cared about precise measurements. Zero quietly improved every one of those activities. From the Islamic world, the new numeral system slowly approached Europe. Its arrival, however, did not immediately produce celebration. In fact, it produced suspicion. Europe had relied on Roman numerals for centuries. Administrators understood them. Church records used them. Legal documents used them. Merchants used them. Changing an entire numerical language was no simple matter. New symbols often inspire distrust.
Many people associated the unfamiliar numerals with foreign cultures. Some believed they made fraud easier, because digits could supposedly be altered more easily than Roman letters. Several cities temporarily restricted or discouraged their use in official documents. Resistance was not based solely on mathematics. It involved tradition, politics, religion, habit. Every revolutionary idea must eventually confront the simple fact that people grow comfortable with what they already know. One traveler would play an especially important role in changing European opinion, Leonardo of Pisa. Today he is better known by a single nickname, Fibonacci. As a young man, Fibonacci traveled extensively through ports around the Mediterranean, where merchants already used the Hindu-Arabic numeral system. He immediately recognized its extraordinary efficiency. When he returned to Italy, he wrote a book called Liber Abaci, published in the early 13th century.
Rather than presenting abstract philosophy, Fibonacci demonstrated practical advantages. He showed merchants how to calculate profits, how to convert currencies, how to determine interest, how to solve everyday commercial problems more quickly than ever before. His audience was not trying to become mathematicians, they wanted better business tools. Once again, practicality defeated tradition. Generation after generation, merchants discovered that the new numerals simply worked better. Bankers adopted them. Scientists adopted them. Universities gradually began teaching them. Roman numerals did not disappear overnight. For centuries, both systems existed side by side. Even today, Roman numerals survive on clock faces, monuments, movie credits, and the names of kings and popes. But for mathematics, science, engineering, and commerce, the victory of the Hindu-Arabic numeral system became inevitable. Hidden inside that victory was the quiet triumph of zero.
It is remarkable how easily we now overlook its importance.
Children learn the digit before they fully understand its meaning. Adults write it hundreds of times without giving it a second thought. Entire careers in science and engineering pass without anyone stopping to appreciate the extraordinary idea hiding in plain sight. Remove zero from modern civilization, and almost everything begins to unravel. Place value disappears, long multiplication becomes painfully inefficient. Long division becomes vastly more difficult. Algebra loses one of its central reference points. Coordinate geometry cannot place an origin. Calculus struggles to define limits and derivatives. Physics loses equations describing motion and equilibrium. Engineering calculations become cumbersome. Accounting becomes unreliable. Digital technology becomes almost unimaginable. Perhaps nowhere is zero more important today than inside computers. Every photograph stored on a phone.
Every song streamed through headphones. Every satellite orbiting Earth. Every message sent across the internet. Every artificial intelligence model. At the deepest level,
all depend upon combinations of only two symbols, 0 and 1. Billions upon billions of electrical switches constantly change between those two states. Off, on, nothing, something. The very idea that once puzzled philosophers now powers the modern world. Yet the history of numbers was far from over. 0 had transformed arithmetic forever. Negative numbers expanded mathematics in another direction. Irrational numbers revealed that fractions were not enough. Soon mathematicians would discover quantities even stranger than any that had come before. Numbers that could never appear on an ordinary number line. Numbers that seemed impossible. Numbers many scholars dismissed as imaginary. And once again, history would repeat its favorite lesson.
The most unbelievable ideas often become the most indispensable. For thousands of years, numbers had described only one direction: more sheep, more grain, more land, more silver, more stars. Even after humanity accepted 0 as a true number, the familiar landscape of mathematics still had an invisible boundary. The number line ended at nothing. Everything existed on one side, nothing existed beyond it. To ancient people, this felt perfectly reasonable. After all, how could there possibly be less than nothing? Imagine standing inside an empty warehouse. Every crate has been removed. Every shelf stands bare. There is nothing left inside. Could someone remove 5 more crates? Of course not. You cannot remove what no longer exists. The warehouse cannot contain negative crates. That simple observation made negative numbers seem absurd. For centuries, many of the world's greatest thinkers believed they simply could not exist.
Yet everyday life had already discovered something mathematics had not.
Imagine a merchant preparing for a long journey. He borrows 100 silver coins to purchase goods. The money is not a gift. It must eventually be repaid. At the moment he receives the loan, he possesses 100 coins in his hand. But does he truly own them? Not entirely. If another merchant examines his finances honestly, the picture looks very different. He has 100 coins. He also owes 100 coins. His wealth is not positive 100. It is effectively 0. Now imagine that his caravan is attacked. Half of the goods disappear. The remaining merchandise is worth only 50 coins. His debt, however, remains 100. When the accounts are settled, he still owes 50 coins he does not have. He possesses less than nothing. Not physically, financially. The idea sounds strange only because the phrase less than nothing mixes two different kinds of reality.
Physically, the merchant still owns objects. Mathematically, his obligations exceed his assets. The debt is every bit as real as the coins themselves. Long before mathematicians accepted negative numbers, merchants were living with them every day. A debt behaves almost exactly like the opposite of wealth. Receiving money reduces debt. Paying money increases available wealth. The arithmetic works naturally. Only the notation was missing. The first civilization known to treat these opposite quantities systematically was ancient China. By the time Europe was still struggling with Roman numerals, Chinese mathematicians had already developed sophisticated computational methods using counting rods. These rods were simple objects, small bamboo or wooden sticks. Placed on a flat counting board, they represented numbers according to their position. At first glance, the system looked surprisingly physical.
The rods could be moved, grouped, separated, or rearranged while calculations were performed. Instead of writing arithmetic on paper, mathematicians manipulated numbers almost as if they were pieces on a game board. As Chinese mathematics became more advanced, a practical problem emerged. How should gains and losses be distinguished? The solution was elegant. Positive quantities were represented one way, negative quantities another. Historical sources describe several methods. Sometimes positive rods were colored red, while negative rods were black. Other traditions reversed the colors or changed the orientation of the rods instead. The exact appearance mattered less than the underlying idea. For the first time, opposite quantities possessed clear visual identities. A profit looked different from a debt. A surplus looked different from a deficit. This was more than convenient bookkeeping. It was a conceptual breakthrough. Instead of asking whether negative quantities physically existed, Chinese mathematicians asked a different question. Do calculations become more accurate if gains and losses are treated consistently? The answer was yes. Once debts received their own notation, arithmetic suddenly became much simpler. Imagine a merchant recording transactions over several weeks. One day he earns 50 silver coins, the next day he loses 20. Later he earns another 30. Without negative numbers, every calculation requires awkward explanations. One must constantly distinguish between money owned and money owed using words. With signed numbers, everything becomes straightforward. Positive 50, negative 20, positive 30. The final balance emerges naturally. The symbols themselves carry the meaning. Language no longer needs to do all the work. Chinese mathematical texts gradually developed rules that modern students would immediately recognize.
Adding two profits produces a larger profit. Adding two debts produces a larger debt. When a profit meets a debt, they partially cancel one another. The larger quantity determines the final result. These principles were not abstract philosophy. They reflected ordinary commercial life. A merchant with 10 coins who owes 3 is effectively better off than one who owes 20. The arithmetic mirrors reality. Perhaps the most remarkable aspect of this development is how practical it remained. There was no grand philosophical revolution, no lengthy debate about whether negative numbers truly existed. There was simply a recognition that accounting worked better when opposite quantities were treated symmetrically. Mathematics advanced because business demanded efficiency. History had repeated one of its favorite patterns. Again, the greatest mathematical revolutions often begin not inside universities, but inside marketplaces. While merchants balanced ledgers, tax collectors recorded obligations, and administrators managed imperial finances, mathematicians quietly transformed the language of numbers. What had once seemed impossible gradually became ordinary, yet this acceptance was far from universal. Across much of the ancient world, philosophers continued asking uncomfortable questions. What does a negative quantity actually represent? You cannot possess negative sheep. You cannot harvest negative wheat. You cannot build a wall that is negative 10 feet long. Unlike 0, which represented the absence of quantity, negative numbers appeared to describe quantities that somehow existed below absence itself. That idea challenged intuition. Imagine asking someone to picture negative 3 apples. Most people instinctively imagine 3 ordinary apples. Then they mentally attach the word negative. The mind struggles because physical objects resist the concept.
Now imagine asking someone to picture a debt of $3. The image comes much more easily. The debt is invisible, yet perfectly understandable. This difference reveals something profound about mathematics. Numbers no longer needed to describe objects alone. They could describe relationships. A positive number might represent possession. A negative number might represent obligation. Neither required a physical object with a minus sign attached. Instead, numbers became descriptions of states.
This shift fundamentally changed what mathematics was capable of expressing. For thousands of years, arithmetic had been tied closely to counting tangible things. Now it began describing abstract situations, financial balances, directions, temperature, elevation, change itself. The number system was quietly becoming more powerful than the physical world that had originally created it. Indian mathematicians would soon recognize this potential more clearly than anyone else. Building upon ideas already emerging in commerce and astronomy, they began developing systematic rules that unified positive numbers, negative numbers, and zero within a single elegant framework. For the first time, the entire arithmetic of opposite quantities would be written down with remarkable clarity, and those rules would survive almost unchanged into the modern world. Among the scholars who helped transform these practical observations into a coherent mathematical system, one name appears again and again: Brahmagupta. When we encountered him earlier, he introduced rules for working with zero, but his contribution did not stop there. In the 7th century, while much of the world still struggled to understand the very idea of nothing, Brahmagupta also described how positive and negative numbers should interact. His language reflected everyday life. Instead of speaking only about numbers, he spoke about fortunes and debts.
The terminology immediately made the mathematics feel tangible. A fortune represented wealth. A debt represented obligation. Everyone understood the difference. If a merchant possessed 2 fortunes, his wealth increased. If he accumulated 2 debts, his financial burden became heavier. If a fortune met a debt, one partially cancelled the other. The larger quantity determined what remained. Modern algebra expresses these relationships using positive and negative signs. Brahmagupta expressed them using the language of commerce. Different symbols, the same logic. This was one of the earliest moments when arithmetic began to resemble the system students still learn today. The beauty of these rules was not that they were complicated, it was that they were consistent. Consistency is one of the deepest goals of mathematics. Every new idea must fit naturally with everything that came before. When mathematicians discover a new type of number, they do not want to destroy the existing system. They want to extend it. Negative numbers accomplished exactly that. Addition still worked. Subtraction still worked. Patterns continued. Nothing needed to be abandoned. The number system simply grew larger. This pattern has appeared repeatedly throughout history. Whole numbers expanded into fractions. Fractions expanded into irrational numbers. Zero became a genuine number. Now positive numbers expanded into a world containing their opposites. Each expansion preserved the previous one, while making mathematics capable of describing more of reality. Indian mathematics flourished in astronomy as well. Planetary motion required calculations involving changing positions, corrections, and differences. Having a reliable way to represent opposite directions made many computations far more elegant. Again, practical necessity encouraged abstract thinking.
The sky became another classroom for arithmetic. As knowledge traveled westward through Persia into the Islamic world, these mathematical ideas continued evolving. Scholars translated works from Sanskrit into Arabic. Greek mathematics, Persian astronomy, and Indian arithmetic met within the same intellectual tradition. Instead of replacing one another, these traditions combined. Mathematicians compared methods, corrected mistakes, improved algorithms, developed entirely new branches of mathematics. Among them, algebra emerged as one of the greatest achievements. The word itself comes from the Arabic title of a famous work by al-Khwarizmi. His systematic methods for solving equations transformed mathematics forever. Yet even as algebra grew more sophisticated, negative numbers remained controversial. Many equations naturally produced negative answers. The calculations worked perfectly. The logic remained sound. The answers, however, made many scholars uncomfortable. Suppose an equation suggests that the length of a wall equals -12 feet. That cannot be physically correct. Walls do not extend backward into non-existence. Likewise, a basket cannot contain -7 apples. Because geometry dominated much of classical mathematics, quantities were expected to represent measurable objects. Negative values seemed to violate that expectation. As a result, many mathematicians simply ignored them. Some solved equations only if the answers were positive. Others stopped their calculations the moment a negative result appeared. Still others referred to such answers using words like false, absurd, or meaningless. The mathematics itself was not the problem. Interpretation was. History reminds us that accepting a new mathematical object often requires changing intuition more than changing calculation. Europe would become one of the last major centers of mathematics to fully embrace negative numbers.
Even during the Renaissance, when science, art, and engineering flourished, many respected scholars remained skeptical. One of the most influential was René Descartes. Today, he is remembered as one of the founders of analytic geometry. Ironically, he also helped preserve distrust toward negative solutions. When solving equations, Descartes referred to certain negative solutions as false roots. The phrase did not mean that his calculations were incorrect. Rather, he believed those answers lacked genuine physical meaning. If a problem described the length of an object, a negative answer could simply be discarded. In fairness, Descartes was not being irrational. He was working within the assumptions of his time. Most mathematical problems concerned geometry, lines, angles, areas, volumes. These quantities naturally remain positive. Within that context, negative values often seemed unnecessary. Yet mathematics was slowly changing. It was no longer concerned only with measuring objects. It was beginning to describe motion, relationships, forces, finance, navigation. As its scope expanded, negative numbers became increasingly difficult to ignore. Imagine climbing a mountain. Your elevation increases. Now imagine descending into a mine below sea level. Your elevation decreases. Which direction should receive the positive sign? There is nothing sacred about the choice. What matters is consistency. One direction becomes positive, the opposite direction becomes negative. Suddenly, negative numbers no longer represent impossible objects. They represent opposite directions. The same idea appears in temperature. On a warm summer afternoon, a thermometer may read 80 degrees Fahrenheit. Months later, during a harsh winter in northern regions, temperatures may fall below zero. No one believes the air contains negative heat. Instead, the number describes position relative to an agreed reference point. Zero becomes the boundary. Values above it extend one way, values below it extend the other. Exactly the same principle governs financial accounts. A checking account containing $100 represents positive wealth. An overdraft of $100 represents a liability. Neither balance is imaginary. Both accurately describe reality. Little by little, mathematicians realized something profound. Negative numbers were not describing strange physical objects. They were describing relationships between quantities. That insight changed everything. Instead of asking, "Can negative apples exist?" they began asking, "What is this number measuring?" The answer determined whether negative values made sense. Length? Usually not. Debt? Absolutely. Direction? Certainly. Temperature? Of course. The meaning depended on context, Once that distinction became clear, much of the old philosophical resistance began to fade. Still, one final breakthrough remained before negative numbers would become completely natural. Mathematicians needed a way to see them, not as debts, not as temperatures, not as abstract symbols on a page. They needed a picture so simple that every arithmetic rule would suddenly become obvious. That picture would become one of the most powerful visual ideas in all of mathematics: the number line. Imagine standing on a long, perfectly straight road. It stretches farther than you can see in either direction. There are no buildings, no trees, no signs, only the road disappearing into the horizon. Now imagine placing a single marker beneath your feet. This point becomes your reference, your starting position, your home. Call it 0. Nothing magical has happened. The road has not changed, only your way of describing it has. Take one step forward.
You are now at +1. Take another. +2. Continue walking. Every step carries you farther in the same direction. Now return to where you started, back to 0. This time, instead of walking forward, turn around. Take one step. Where are you now? For thousands of years, mathematics struggled with this simple question. Ancient arithmetic had no satisfactory answer. You had moved. Your new position was perfectly real, yet you were not standing at a positive location. You occupied the opposite side of the starting point. The simplest description was also the most revolutionary. -1. Walk another step. -2. Suddenly, negative numbers no longer seemed mysterious. They were not invisible objects. They were positions. The invention of the number line transformed mathematics in a profound way. Before it, numbers were often imagined as collections of things. 3 sheep, 5 stones, 10 coins. Now numbers became locations. The difference may sound subtle. In reality, it changed everything. Locations naturally extend in 2 directions. There is no reason a road should stop at 0. There is no invisible wall preventing movement beyond the origin. The same logic applies to countless situations in everyday life. Imagine standing on a beach at sea level. A helicopter rises 500 feet into the air. Its altitude is positive. Now imagine a submarine diving beneath the surface. Its depth is naturally described using negative values. Neither vehicle behaves strangely. They simply occupy opposite sides of the same reference point. The mathematics becomes almost effortless. Temperature provides another familiar example. Long before thermometers existed, people understood that winter was colder than summer. Eventually, scientists created numerical scales to measure heat. Once again, they selected a convenient reference point. Temperatures above that point became positive.
Temperatures below it became negative.
There is nothing mysterious about -10 degrees. The air does not contain less than nothing. The number simply indicates position below the chosen reference. Bank accounts tell the same story. Suppose you have $500 saved. Your balance is positive. Unexpected expenses arrive. Eventually, you owe the bank $200. Your balance becomes negative. No one imagines that negative money physically exists inside the account. Instead, the number describes your financial relationship with the bank. The account has crossed 0. Exactly like walking across the origin on the number line. Engineers think this way. Economists think this way. Physicists think this way. Pilots think this way. Even video game designers think this way. Whenever something can move in opposite directions from a reference point, negative numbers become the natural language for describing it.
Once mathematicians accepted this perspective,
Many old arithmetic rules suddenly became obvious. Consider addition. If you stand at +3 and walk 2 steps forward, you arrive at +5. Simple enough. Now begin at +3, but walk 2 steps backward. You arrive at +1. Adding a negative number is simply moving in the opposite direction. Subtraction becomes equally intuitive. Subtracting a positive quantity means moving left. Subtracting a negative quantity means removing movement to the left. That is exactly why subtracting a negative value sends you to the right. Students often memorize this rule without understanding it. On the number line, it almost explains itself. Even multiplication becomes less mysterious. Repeated addition shows why positive multiplied by positive remains positive. Repeated movement in the opposite direction explains why a positive multiplied by a negative becomes negative.
The final rule puzzled mathematicians for centuries. Why should a negative multiplied by another negative produce a positive? The answer does not come from physical objects. It comes from consistency. Mathematics is built upon patterns. Once the earlier rules are accepted, only one possible answer preserves every existing relationship. A negative multiplied by a negative must become positive. Otherwise, familiar arithmetic identities begin contradicting one another. The result is not an arbitrary decision. It is the only choice that keeps the entire numerical system internally consistent. This realization marked another important shift in mathematical thinking. The goal was no longer to imitate physical reality at every step. Instead, mathematics sought logical consistency. If a new concept fit perfectly into the existing framework while describing the world more effectively, it deserved acceptance. That philosophy would guide nearly every major mathematical discovery that followed. The history of negative numbers illustrates an important lesson. Human intuition is not always the best guide to mathematical truth. For centuries, scholars rejected negative numbers because they felt unnatural. Today, children encounter them before reaching middle school. The strange became ordinary. Exactly as 0 had before, exactly as irrational numbers would, exactly as imaginary numbers eventually would. Each generation inherits ideas that earlier generations considered impossible. Perhaps that is one of the most remarkable features of mathematics. Its boundaries are never fixed. Every time humanity believes the number system is complete, reality asks a new question. Every time intuition declares, "That cannot possibly be a number," mathematics quietly replies, "Let's see." By now, the number system had expanded dramatically. Humanity could count objects, describe fractions, represent nothing, measure gains and losses, move freely in opposite directions. The mathematical universe had become larger than anyone living in ancient Egypt or Babylon could have imagined. Yet another surprise was already waiting. The next challenge would not emerge from commerce, or accounting, or navigation. It would arise from one of the oldest branches of mathematics itself: geometry. A simple square, 4 equal sides, 1 diagonal. Nothing could appear more ordinary. And yet hidden inside that diagonal was a number unlike any humanity had ever seen. A number that could never be written as a fraction. A number whose decimal expansion would continue forever without repeating. A number that shattered one of the oldest beliefs in mathematics and forced humanity to rethink the very meaning of number once again. By this point in our story, the history of numbers almost seems predictable. A civilization encounters a problem.
The existing number system proves too limited. Mathematicians resist change at first. Eventually, a new kind of number emerges. What once appeared impossible slowly becomes indispensable. This pattern had repeated itself with 0. It had repeated itself with negative numbers. The next revolution, however, would be unlike anything before it. Earlier discoveries had grown out of practical life. Merchants needed better accounting.
Governments needed better records. Astronomers needed more accurate calculations. This time, the crisis would emerge from something far more unexpected: a simple geometric shape. Imagine drawing a perfect square. Nothing could appear more ordinary. 4 equal sides, 4 right angles. A figure so familiar that children recognize it almost as soon as they learn to draw. Now suppose each side measures exactly 1 unit. The square seems completely understood. Its perimeter is easy to calculate. Its area is obvious.
Every measurement appears neat and orderly. Then draw a single line from one corner to the opposite corner, the diagonal. At first glance, nothing remarkable has happened. It is simply another line. Yet hidden inside that ordinary-looking segment lies one of the greatest discoveries in mathematical history. To understand why, we need to travel back more than 2,500 years to ancient Greece. The Greek world inherited mathematical ideas from Egypt and Mesopotamia, but it approached them differently. Earlier civilizations had largely treated mathematics as a practical tool. The Greeks wanted something more. They wanted certainty, not rules that merely seemed to work, proofs that could never fail. Rather than asking how to calculate, they asked why calculations worked in the first place. This shift transformed mathematics forever. Instead of collecting recipes, they began constructing logical systems. Every statement had to follow from previous statements. Every conclusion required proof. Among the many philosophical communities of ancient Greece, one became especially influential: the followers of Pythagoras. Today, nearly everyone recognizes his name because of the famous theorem relating the sides of a right triangle. Yet the Pythagorean school was much more than a group of mathematicians. It was part scientific academy, part philosophical society, and part religious brotherhood. Its members believed that numbers revealed the hidden structure of reality. Music demonstrated this beautifully. Stretch a string. Pluck it. Now shorten it by exactly half. The pitch rises by 1 octave. Simple numerical ratios create harmonious sounds. The same principle appears throughout music. Pleasant intervals correspond to elegant numerical relationships. To the Pythagoreans, this could not be a coincidence. They concluded that the universe itself must be built upon whole numbers and their ratios. Harmony, motion, geometry, nature. Everything seemed governed by simple relationships between integers. It was an inspiring vision. Elegant, orderly, complete. Then geometry asked a question that shattered it. Consider our square again. Each side measures exactly 1 unit. How long is the diagonal? Using the theorem now associated with Pythagoras, the answer appears immediately. The square built upon the diagonal must have the same area as the 2 smaller squares built upon the sides. 1 plus 1 equals 2. Therefore, the diagonal must have a length equal to the square root of 2. At first, this seems perfectly acceptable, but the Pythagoreans wanted something more specific. Surely this new length could be written as a fraction. After all, every measurable quantity should be expressible as the ratio of 2 whole numbers. That belief formed the foundation of their worldview. So they searched. Perhaps the diagonal was 3 halves. No. Perhaps 7/5. Still not. Maybe 99/70ths. Closer, but not exact. Larger fractions produced better approximations. Hundreds, thousands, millions. The estimates approached the true value more and more closely. Yet they never reached it. At first, this might not have seemed alarming. Perhaps nobody had searched far enough. Perhaps the correct fraction was simply very complicated. Then came one of the most beautiful proofs in all of mathematics. Instead of searching endlessly for the correct fraction, Greek mathematicians asked a different question. What if no such fraction exists? The proof begins with a bold assumption. Suppose the square root of 2 really can be written as a fraction. Assume that fraction has already been simplified as much as possible. Its numerator and denominator share no common factors.
Now square both sides. Carefully follow the arithmetic. Eventually, something impossible happens. The proof demonstrates that both the numerator and the denominator would have to be even numbers. But if both are even, then the fraction was never fully simplified. That contradicts the original assumption. The contradiction leaves only one possible conclusion. The assumption itself must be false. No fraction can ever equal the square root of 2. The diagonal of a simple square cannot be expressed as the ratio of 2 whole numbers. Today, this proof appears in countless mathematics textbooks. To the ancient Greeks, however, it was devastating. One ordinary geometric figure had destroyed an entire philosophical vision of reality. The implications reached far beyond geometry. If the diagonal could not be written as a ratio, what did that mean? Was it still a number, or something entirely different? The Greeks called such quantities allegos, meaning without ratio. Centuries later, the Latin term irrational became standard. The modern word often causes confusion. Outside mathematics, irrational usually means unreasonable or illogical. Here it means something completely different. An irrational number is simply one that cannot be written as the ratio of 2 integers. Nothing more, nothing less. The number itself behaves perfectly logically. Its decimal expansion simply never ends and never settles into a repeating pattern. Write more digits, there are always more waiting. Unlike familiar fractions such as 1/2 or 3/4, no exact endpoint exists. The decimal representation continues forever. Perhaps the most famous story connected with this discovery concerns a man named Hippasus. According to later tradition, Hippasus revealed the existence of irrational quantities outside the secret teachings of the Pythagorean Brotherhood. Some versions of the legend claim he was cast into the sea by his fellow Pythagoreans. Others say the gods themselves punished him with a shipwreck. Modern historians cannot confirm whether any of these stories actually happened. The evidence is uncertain. The legend may have grown over centuries, yet the fact that such stories survived tells us something important. People remembered this discovery not as an ordinary mathematical result, but as a profound intellectual shock. Whether Hippasus truly paid with his life is less important than what the legend symbolizes. Ideas powerful enough to overturn an entire worldview often inspire fear before they inspire understanding. The Pythagoreans believed numbers explained reality. Ironically, it was another number that challenged everything they believed. Instead of abandoning mathematics, Greek scholars adapted. If arithmetic could not comfortably contain these strange quantities, perhaps geometry could. A line segment could certainly have the length of the square root of 2. You could draw it, measure it, construct it, even if you could never write it as a fraction. For centuries, geometry became the natural home of irrational quantities. They existed not primarily as numbers but as lengths. The crisis had been postponed, not solved. Eventually, mathematicians would realize that these mysterious quantities deserved full citizenship within the number system itself. And once that happened, entirely new irrational numbers would begin appearing everywhere, in circles,
in exponential growth, in probability, and in the deepest laws governing the universe. For a long time, the square root of 2 appeared to be a strange exception. Perhaps, mathematicians wondered, it was the only number of its kind. Perhaps irrational numbers were rare curiosities hiding inside unusual geometric figures. History would reveal something far more astonishing. They were everywhere. The first clue came from a shape even more familiar than the square: the circle. Long before written mathematics existed, people noticed a remarkable pattern. No matter how large or small a circle became, one relationship never changed. Measure the distance around the circle, then measure the distance across its center. The ratio between those two lengths always remained the same. Today we call that constant pi. Children usually encounter it as approximately 3.14. Scientists often use more digits. Computers can calculate trillions of them. Yet no matter how many digits are produced, the decimal expansion never reaches an end, nor does it begin repeating. Like the square root of 2, pi refuses to become a fraction. At first, civilizations relied on practical approximations. The ancient Babylonians used a value close to 3 1/8. Egyptian scribes developed an approximation that was surprisingly accurate for its time. These values worked well enough for construction, engineering, and everyday life. No one expected absolute perfection. Then came one of the greatest mathematicians of the ancient world, Archimedes of Syracuse. Living during the 3rd century before the Common Era, Archimedes approached the problem with extraordinary creativity. Instead of trying to calculate the circumference directly, he surrounded a circle with polygons, first 6 sides, then 12, then 24. Again and again he doubled the number of sides. As the polygons became more refined, they hugged the circle more closely. One polygon lay inside the circle, another surrounded it. The true circumference had to fall somewhere between them. By squeezing the answer between increasingly accurate bounds, Archimedes produced the finest estimate of pi the ancient world had ever seen. His method was brilliant not simply because it worked. It demonstrated a new style of mathematical thinking. Sometimes an exact answer remains unreachable, yet it can still be approached as closely as desired. This idea would later become one of the foundations of calculus. For centuries afterward, mathematicians continued chasing additional digits. 10 digits, 100, 1,000, eventually millions. Today, computers calculate trillions. Still, the pattern never repeats. Pi continues without end. If you were somehow able to write one new digit every second without sleeping, eating, or stopping for any reason, your entire lifetime would barely scratch its endless expansion. Yet despite its infinite decimal representation, pi appears in remarkably ordinary places. Every wheel, every coin, every planet, every soap bubble, every orbit, every rotating machine, every circular ripple spreading across a quiet lake. Wherever circles exist, pi quietly waits beneath the surface. The universe seemed strangely fond of this mysterious number. Then another unexpected constant emerged. Unlike pi, it was not born from geometry. It arose from growth. Imagine depositing $1 into a bank account that earns 100% annual interest. If the bank adds all the interest at the end of the year, you finish with $2. Simple enough. But suppose the interest is added twice each year instead. Now the calculation changes slightly. What if it is added every month, every day, every hour, every minute? As the compounding becomes more frequent, something surprising happens. The final balance keeps increasing, but only by smaller and smaller amounts. Eventually, the value approaches a very specific number. That number is known today as e. Like pi, its decimal expansion continues forever without repeating.
Unlike pi, it emerged not from circles but from continuous growth. At first glance, e seems far less famous. Most people encounter pi in school. Few think about e outside mathematics or science. Yet it governs an astonishing range of natural phenomena: population growth, radioactive decay,
Compound interest, chemical reactions, probability, the spread of disease, electrical circuits, even many processes inside living cells. Whenever change occurs continuously rather than in sudden jumps, E often appears. Nature seems to favor it just as strongly as it favors pi. By now, a curious pattern had emerged. The first irrational number appeared unexpectedly inside a square. Another governed every circle. A third described continuous growth. The more mathematicians explored, the more irrational numbers they discovered. Eventually, an even deeper question arose. How many irrational numbers actually exist? At first, the obvious answer seemed to be many. The true answer proved almost unimaginable. Consider all the fractions: 1/2, 3/4, 5/7. Even though there are infinitely many fractions, they remain surprisingly sparse. Between any two fractions, another fraction always exists. Yet irrational numbers fill the gaps with overwhelming abundance. Choose almost any point on the number line. The probability that it represents an irrational number is vastly greater than the probability that it represents a rational one. In a very real sense, rational numbers form tiny islands floating inside an endless ocean of irrational values. This realization completely reversed humanity's original intuition. For thousands of years, fractions had seemed to represent the normal kind of number. Irrational numbers looked like rare exceptions. Modern mathematics revealed the opposite. The exceptions were the fractions. The overwhelming majority of numbers are irrational. Imagine the entire number line stretching endlessly in both directions. Every point corresponds to exactly one real number. Some of those points represent familiar fractions. Most do not. The line itself is perfectly continuous. There are no tiny gaps waiting to be filled. Every imaginable position already belongs to some number. This continuity became one of the greatest achievements of modern mathematics. It unified arithmetic and geometry completely. Numbers no longer merely counted objects. They described every possible location along an unbroken continuum. Ironically, despite this theoretical perfection, computers cannot store irrational numbers exactly. No digital machine, no matter how powerful, can write infinitely many digits. Instead, every calculator, every smartphone, every scientific simulation uses approximations. When your calculator displays pi, it is quietly hiding countless missing digits. When engineers calculate the orbit of a spacecraft, they use values accurate enough for the task at hand. Not because mathematics lacks precision, because physical computers possess finite memory. Reality itself rarely requires infinite decimal expansions. Extraordinary accuracy is usually sufficient. This distinction between exact mathematics and practical computation has become one of the defining features of modern science. The equations remain perfect. The calculations become approximations. And yet those approximations guide spacecraft across billions of miles, predict eclipses centuries in advance, and allow smartphones to determine your location within a few feet, almost anywhere on Earth. The success is extraordinary. Still, even irrational numbers would not mark the end of humanity's expanding numerical universe. Another mystery was already beginning to appear inside algebra. Equations that should have had perfectly ordinary solutions sometimes demanded something impossible: a square root of a negative number.
For centuries, mathematicians dismissed such expressions as nonsense. Then a handful of remarkably stubborn thinkers decided to ask a dangerous question. What if these impossible numbers deserve to exist too?
If there is one lesson repeated throughout the history of numbers, it is this. The most revolutionary ideas almost always begin as impossible ones. 0 seemed impossible. Negative numbers seemed impossible. Irrational numbers seemed impossible. Now mathematics faced another obstacle. Imagine solving one of the simplest equations imaginable. What number multiplied by itself equals 9? The answer is obvious. 3. Or -3. Now change the equation. What number multiplied by itself equals -1? The room suddenly becomes quiet. Every positive number becomes positive when squared. Every negative number also becomes positive when squared. No matter how many ordinary numbers you try, none can satisfy the equation. For centuries, mathematicians reached exactly the same conclusion. The equation had no answer, or rather, no answer that anyone was willing to accept. Yet, during the Renaissance, algebra was advancing at an astonishing pace.
Italian mathematicians competed fiercely to solve increasingly difficult equations. Public mathematical contests attracted enormous attention. A successful method could bring wealth, prestige, and powerful patrons. Keeping new discoveries secret became common practice. Among the greatest breakthroughs was the solution of cubic equations. Names such as Scipione del Ferro, Niccolo Tartaglia, and Girolamo Cardano became permanently linked to this achievement. Cardano eventually published these methods in his famous book, Ars Magna. The work transformed European algebra, but hidden inside several perfectly valid calculations was something deeply unsettling. Sometimes the path toward an ordinary real answer passed through expressions involving the square root of a negative number. Imagine climbing a mountain only to discover that the trail briefly disappears beneath the ground before emerging safely on the other side. The destination is perfectly real. The journey seems impossible. That was exactly how these equations behaved. Mathematicians could often verify that the final answer was correct, yet the intermediate calculations appeared meaningless. Many scholars responded by simply ignoring these mysterious expressions. If they appeared during a calculation, they were treated as formal tricks rather than genuine numbers. Others believed the equations themselves must somehow be defective. The strange symbols felt like mathematical ghosts, present in the calculation, absent from reality. Then, an Italian engineer and mathematician named Raphael Bombelli made a remarkable decision. Instead of avoiding these impossible quantities, he decided to study them. Bombelli realized something important. Even if these strange expressions did not correspond to ordinary numbers, perhaps they still followed consistent rules. Suppose they could be added, subtracted, multiplied, simplified. Would algebra become more coherent? Patiently, Bombelli began exploring exactly that possibility. He developed systematic rules describing how these mysterious quantities should behave. Many of those rules remain essentially unchanged today. His work did not immediately convince everyone, far from it. Most mathematicians still regarded the new numbers with suspicion. Yet Bombelli had demonstrated something profound. Consistency sometimes matters more than intuition. If a new mathematical object preserves the logical structure of the entire system, perhaps it deserves to exist. The breakthrough arrived gradually over the following centuries. Eventually, mathematicians introduced a simple symbol for the square root of -1. Today we call it I. By definition, I multiplied by itself equals -1. At first glance, this seems like cheating. Instead of discovering a number, it appears as though mathematicians simply invented one. In a sense, they did. But invention has always been part of mathematics. Zero was invented. Negative numbers were invented. Coordinate systems were invented. The important question is not whether an idea is invented, it is whether the invention reveals genuine patterns that describe reality. Again and again, imaginary numbers proved that they did. The name itself, however, created lasting confusion. The term imaginary number was introduced partly because these quantities seemed unreal compared with familiar numbers. Unfortunately, the label survived long after mathematicians understood their importance. Nothing about imaginary numbers is imaginary in the everyday sense. They obey precise rules. They produce experimentally verified predictions. Engineers rely upon them every day. In many areas of science, they are just as indispensable as ordinary numbers. The true conceptual breakthrough came when mathematicians stopped trying to squeeze every number onto a single straight line. Real numbers occupy one dimension, positive to the right, negative to the left. Imaginary numbers required an entirely new direction. Instead of extending the number line, they created the complex plane. Imagine drawing two roads crossing at right angles. The familiar horizontal road contains the real numbers. The new vertical road contains the imaginary numbers. Every point on this plane represents a unique combination of both. Suddenly, numbers became locations in two dimensions. This geometric picture transformed an abstract idea into something almost tangible. One of the greatest champions of this viewpoint was Carl Friedrich Gauss, often called the Prince of Mathematicians. Gauss demonstrated that complex numbers were not strange exceptions, but natural extensions of the numerical world. His work helped persuade generations of mathematicians that complex numbers deserved full acceptance. Another giant soon entered the story: Leonhard Euler. Few mathematicians have influenced modern science more profoundly. His notation appears throughout mathematics even today. Euler revealed astonishing relationships connecting seemingly unrelated constants: 0, 1, pi, the imaginary unit, exponential growth. His famous identity, e raised to the power of I times pi plus 1 equals 0, has often been described as one of the most beautiful equations ever discovered. It links 5 of mathematics' most fundamental constants within a single, elegant statement. What once appeared impossible had become breathtakingly harmonious. By the 19th century, complex numbers were no longer philosophical curiosities. They had become practical tools. Electrical engineers discovered that alternating current becomes dramatically easier to analyze using complex arithmetic. Physicists found that wave motion naturally follows the same mathematical language. Quantum mechanics, the theory describing atoms and subatomic particles, depends heavily upon complex numbers. Signal processing, radio communication, medical imaging, control systems, modern telecommunications. Every one of these fields relies upon mathematics that earlier generations dismissed as nonsense. Even the device on which you may be listening to this story owes part of its existence to imaginary numbers. Designing microprocessors, modeling electromagnetic fields, compressing audio, transmitting wireless signals, all become vastly simpler through complex analysis. The irony is difficult to miss. The numbers, once considered the least realistic, eventually became essential for building some of humanity's most advanced technologies. Looking back across thousands of years, a remarkable pattern emerges. Humanity began with simple counting. 1 sheep, 2 sheep, 3 sheep. Numbers described objects that could be touched. Gradually, they expanded.
Fractions described parts of wholes. 0 described absence. Negative numbers described opposition. Irrational numbers described continuous geometry. Complex numbers described structures hidden far beyond ordinary intuition.
At every stage, mathematics became less about counting objects and more about describing relationships. Today, when physicists study black holes, when economists model financial markets, when biologists analyze genetic information, or when engineers design spacecraft, they all speak the same universal language, the language of numbers. Not because numbers exist independently inside nature, waiting to be discovered exactly as we write them, but because generation after generation, humanity has refined them into an increasingly powerful system for recognizing patterns. That may be the greatest achievement in the entire history of mathematics. Numbers did not merely help us count the world, they taught us how to understand it.
And perhaps the most extraordinary part of the story is this. No one knows whether it has truly ended. Every previous generation believed the number system was nearly complete. Every previous generation was wrong. Somewhere in the mathematics of tomorrow, another impossible idea may already be waiting. An idea that seems absurd today, an idea future students will one day consider completely